torque is the rotational analog of force, meaning that when force was what was required to cause an acceleration on something, torque is a force applied to cause an angular acceleration. A force applied that causes an angular acceleration. An angular acceleration. All right, so in terms of rotation so far, we basically just talked about rotational kinematics and how things can speed up or slow down in their spinning. And working through that, really that's just an extension of what happens under Newton's first law for rotation. Where Newton's first law was an object in motion stays in motion, an object at rest stays at rest, unless acted upon by an outside force. We saw with linear motion that objects in motion stayed in motion unless there was something causing an acceleration. Well, then we translated that to rotation, and we saw that spinning objects continued to spin unless something was causing them to speed up or slow down, in which case they changed their angular velocity. Well, now we're going to look at Newton's second law for rotation. Newton's second law for rotation. Now, Newton's second law for linear motion, what was that? F equals ma. Pretty easy. Well, now we're going to translate this in terms of rotation. So we're going to take each of these values and just like when we put them here, we're going to divide the linear value by r, and we're going to wind up with the rotational value. So for force, we're now going to talk about torque. And instead of mass, we're going to talk about rotational inertia, which is I. Hey, I for inertia, that's actually finally one that makes sense. And angular acceleration is alpha. So torque, that is tau, yeah. Yeah, it's a squiggly T. Rotational inertia. Just wait till we get to angular momentum. We'll have all sorts of phrases there about fishing. Tau. Yep. Yes. All right. Now, when we applied Newton's second law, what kind of forces could we identify as ma? What kind of forces could we set equal to ma? Say again? Net forces. So we could use F equals ma only for net forces, correct? Well, the same applies for tau. We can only apply torque equals I alpha for net torques. So this worked for net forces. This works for net torques. Now, when we learned Newton's second law, m was pretty easy. It's the mass of an object. Acceleration we'd already been talking about. Well, over here we've already been talking about angular acceleration, but we haven't talked any bit about rotational inertia. So before we can really go any further, we've got to figure out, well, what is rotational inertia? So rotational inertia. Anybody want to take a stab at a definition for rotational inertia? How resistant something is to spinning? Anybody else? Inertia held rotationally. Tendency to stay spinning. All right, so I actually like a combination of Admir and Nathan's definitions because you each got half of it. Where inertia was just an object's tendency to resist a change in motion. We've got to talk about the fact that it's both trying to avoid changing its angular velocity and that it's trying to avoid starting its angular velocity. So rotational inertia is an object's tendency to resist a change in angular velocity. Right. Doesn't matter what kind of change, it's any change. And the values that actually go into determining this are the object's mass and how that mass is positioned around a rotational axis. So this is determined by an object's mass and where the mass is positioned with relation to its axis. A couple of things we've got here. These are a metal ring and a plastic disc, which have the exact same mass. So note, the only thing that is different about these is, well, what material they're made out of, and where the mass is relative to the axis. They've got the same amount of mass. Now, the way we can see that one resists rotating better than the other is by trying to roll them down a hill. So previously, and this is going to actually touch on some of your guys' two-dimensional momentum collision labs, we tried to, actually this board worked? This board has worked, I'm going to use a different one. We tried to roll ball bearings down a hill, and we said that the mass of those objects didn't matter. They were always going to roll at the same speed when they reached the bottom. Well, that's true, the mass didn't matter. But how the mass is distributed does matter. So I'm actually going to have a board up here. I know these ones aren't warped like that. And what I'm going to do is I'm just going to have these two discs, or the hoop and the disc, roll down the hill, and I want you to take a guess real quick which one's going to make it to the bottom first. Which one's going to make it to the bottom first? Why? Okay, weight's further away from the axis, so metal one will make it to the bottom. Reasoning from someone from the plastic one. Okay, I'm not sure that's a physics-related answer, but it's right. Okay. All right, so just watching to see which one makes it to the bottom first. Clearly the black disc, correct? Okay, so while Ed was right about the black one making it to the bottom first, I'm not sure his reasoning was valid. Just thinking maybe there could be something else here. So Lily's reasoning, while it led her to the wrong conclusion, the reasoning was right. The mass is all located towards the outer portion of the ring. Therefore, it has a higher rotational inertia, meaning it has a higher tendency to resist a change in angular velocity. So, while both objects have the same amount of mass, it took more time for this one to begin, or to get to that rotational velocity, or to make it down the hill, because it didn't have the same angular acceleration. Yeah.
Would it roll for a longer period though? Because it's hard for it to stop.
Would it roll for a longer period? That's because this one got picked up. Yeah, it would roll for a longer period because it would take more effort to get it to slow down. And just let them go. All right, so talking rotational inertia, I is always proportional. Is that the symbol for proportional? I use it like that. It's congruent. What's the symbol for proportional?
No, isn't it?
So don't do a third squiggle. I'm looking for a proportional. It's 3 straight lines.
No, I'm pretty sure that's congruent.
Proportional is like, according to the online, it's like the angle acceleration.
Oh, I'm not going to use that because that's going to be super confusing. All right, then I'm just going to stick with this as proportional to, even though it's mathematically not sound, because I'm not using the thing that looks like alpha, because that would be worse. So I is proportional to mr squared. So regardless of what object we're talking about, as mass increases, rotational inertia increases. As radius increases, rotational inertia increases dramatically. Okay? Technically, calculus students, this is actually I is proportional. I'm going to use that for proportional to the integral of, I'm just trying to think about it, mr, and I believe it's like half mr. Why? Okay, so for calculus students, why would this being an integral matter? Okay, because we're solving for the area over which, and I should say dr. Okay, because we're solving for over which the area that the radius is distributing the mass. And I would solve for this from 0 to r. However, that would solve nicely for this disk. However, it won't solve very nicely for this ring because there is no mass located at 0. So actually to solve for this one, I'd want to solve for from the inner r to the outer r, and thus increase the total value of my rotational inertia. Fortunately, we don't have to worry about actually calculating rotational inertias. We're going to use a chart that tells us what they are. So, pulling up so conveniently, I Google rotational inertia, and it's like the second image that pops up. The image that I use comes right from Hyperphysics, which is linked in your syllabus. Handful of different shapes and the rotational inertias. I've got like 4 side conversations going. Are we confused about something, discussing something relevant, or just acting like it's Tuesday? Okay. So, objects that we see here. Now, these different coefficients, these fractions, all come from how that integral actually plays out, depending on the distribution of the mass throughout the object. So for this first one, a solid disk about its axis of symmetry, well, that's this object. Half times its mass times its radius from the center out is the rotation, or squared is the rotational inertia of this object. I could also take it, and I could, instead of spinning it this way, I could spin it this way. And doing that, you change the rotational inertia because you change how the mass is distributed around that axis. And now instead of just being half mr squared, instead it's a quarter mr squared. And now how long this is begins to matter. So if you were to think about like spinning an oil drum around it, or a 55-gallon barrel around an axis like this, now it would matter how long that object is. Good with that idea? Length, think tubes. Okay. Next one up, hoop about an axis of symmetry. We can either talk about that metal one that we just had, or for the purpose of demonstration, I have hula hoops, so I may as well use it. Hula hoops about this axis where you would normally hula them. Actually, that's a little bit offset. I think I said hula them. Yeah. I would assume so. Or do you hoop? No, I think hooping is like basketball. All right. So your attention is back here. Your attention is back here. Oh, you guys are on one today. So, hoop about an axis of symmetry, mr squared. Hoop spinning like this, 1/2 mr squared. Solid sphere. So think a bowling ball, 2/5 mr squared. It doesn't matter where the axis is placed because it's a symmetrical sphere. Thin spherical shell, 2/3 mr squared. Example of a thin spherical shell? Tennis ball, basketball, soccer ball, any sports ball other than a football, which has its weird own shape. Next one over here, rod about a center. That could be a pencil. It could be a meter stick. And then rod about an end would be here. Or I'm sure like probably at least half of you have taken a meter stick and spun it around like this at some point. A baseball bat, yeah, that would be good.
So it doesn't have to be perfect.
No, it doesn't. Because what's important about it is that it's a distribution of mass from that location. And the variations from there are pretty trivial. Reasons I'm going through each of these, while I'm going to provide you with rotational inertias for standard objects, in any given problem, you've got to assess what kind of object it's going to be. If I have a problem for you about a bowling ball, you have to assess the bowling ball to be a solid sphere and not a hoop about the diameter. Makes sense? Bowling balls are actually solid. No, you can break the bowling ball open. Yeah, that's what I'm saying. Hey guys, I need to be able to hear. It does, and I'm not going to give you one of those. I'm only going to give you things that fit with reasonable approximation to these objects. I say with reasonable approximation because holes in a bowling ball. Okay. Technically, every object has its own rotational inertia. These are just basic shapes. Okay, things that should include most objects we could encounter. Questions about any of these rotational inertias? No? Okay. So, now I've got stuff all over my desk here. You could. All right. So, rotational inertia is an object's tendency to resist a change in motion and rotation, and that depends on its mass and its radius that the mass is distributed about. The only other one that I am going to expect you to remember is that for a point mass, I is equal to mr squared. Note that I'm not saying proportional, I am saying equal for a point mass. Okay, well, what is a point mass? There are two ways, no, there's only one good way to interpret the point mass. A point mass is an object in circular motion, not rotational motion. What's that distinction mean? It's orbiting. That's a good way to say it. Yeah, when we talk angular momentum later this week, we'll talk about planets, and the planets have a rotational inertia of mr squared when we are talking about their orbits around the sun. Alternatively, if we don't want to talk about planets orbiting, we can talk about a person on a merry-go-round. A person on a merry-go-round has a specific rotational inertia based on that person's mass and where they are standing on the merry-go-round relative to the axis of rotation of the merry-go-round. Note, when I say merry-go-round, I'm talking about those toys that they've been removing from playgrounds, not a carousel. Okay? They are fun. All right. Having discussed rotational inertia and developed the definition for that, we can now apply that to our understanding of torque. Torque is basically treated how forces are. We can try to determine how fast or slow something is going to accelerate simply using our understanding of torque. So I'm just going to go ahead and jump in with an example here, and I'm going to stick with merry-go-rounds. And we're going to put a person on this merry-go-round. Okay? Let me think about how I want to arrange this. Yeah, we'll take the person off the merry-go-round to begin with, and they'll just spin it. Okay? So, a merry-go-round is spinning at, let's say, half a rotation per second. Per second. In order to bring the merry-go-round to a stop, in, let's say, 5 seconds, what torque must a person apply? Now, this is going to be dependent upon the type of merry-go-round, and we're going to assign our merry-go-round a mass of 100 kilograms and a radius of, let's say, 2 meters. Okay? So to start something like this, it's going to look a lot like problems you've already solved. What are you going to use? What do you need to find first? If you want to find angular acceleration. So we're going to find angular acceleration using the angular kinematics we've already been working with. So go ahead, take a minute, do that. All right. Questions about torque in this kind of situation? I believe of angular momentum. I'd have to double check that, but it might be the other way around. So this problem in terms of torque only looked at one torque being applied to the scenario. We could talk about this also now in terms of, let's say, hey, there was friction acting here, and friction's trying to slow it down. In terms of this line here, where we're talking finding the net torque, this could be torque 1 plus torque 2, etc., equals I alpha. This could be the person. This could be some kind of friction about the axis. We could add another person here who's trying to help them out. Whatever the various torques are that sum up to that I alpha value. Regardless of how many torques are acting on this situation, this would be what we call a dynamic situation. Dynamics meaning things are moving. Now, the alternative to working with torque in things that are moving is pretty obvious. Torque in terms of things that aren't moving, or things that we really don't want to have be moving. One example for that would be a window washer's scaffolding. So, if you have ever watched one of those movies where they're cleaning the windows to a skyscraper, or maybe you've actually been to a city and watched them clean the windows on a skyscraper, where they like lower from the roof and they're on some kind of like, almost it's a cart that's supported by a couple of cables. And the guy stands over here and he washes the windows, right? This is why I'm not an art teacher. And maybe there's a second person, or maybe he's got like some kind of equipment. And we'll put a barrel here. for equipment. Well, really, it'd be like more like a garbage can, I'm thinking. I don't know. For water, yeah. Okay? If you need a lot of it. So, what we'd be looking at here, if I just wanted to talk about this setup in terms of forces, what forces could I identify acting on the scaffolding itself, meaning the thing that these people are standing on? Tension, where?
On the ropes.
On the ropes. All right, so I'm going to draw force tension 1, and I'm going to draw force tension 2. What other forces would be acting on this scaffolding? Gravity.
And normal.
Normal forces act. What do you mean?
Like against gravity.
Don't you need to be resting on something for that? Okay, so the scaffolding is applying a normal force to the person and the garbage can, but normal force is not being applied from them, but their gravity forces are applying here. I'm going to say force gravity person and force gravity can. All right, so if we had a forces problem, we would now go through and we would say that the net force, F net, in the vertical, acting on the scaffolding, would be equal to force tension 1 plus force tension 2 minus force gravity of the can minus force gravity of the person minus force gravity of the scaffolding. And hopefully this is going to be equal to what? Because if it's not, what happens? Well, we're accelerating. Maybe it's moving up accelerating, maybe it's moving down accelerating, but we want to be able to say that it's equal to 0. Now, solving this with forces, we encounter a problem. Looking at the scenario here, how can I determine, let's say I give you the masses of each of these objects. Let's say this is 50 kilograms, the person's 100 kilograms. Really? I didn't, oh. It's about my mass. And then the scaffolding itself, let's say, is also 100 kilograms. So, all right. If I give you the masses, though, here, what's the issue? What are we going to have a problem with trying to solve this? Why? There's 2 of them. Because there are 2 of them, we'd need another equation. We'd need some other kind of information in order to figure out how much tension's in each of these cables. Now, if it's like one cable that's looped up and over something, sure, it's going to balance out, it's going to be equal. But if these are 2 separate cables, we need more information in order to figure this out with forces. But if we use torques, we just need to know where things are. So for this problem, we can figure out where things are, and we'll just assign some distances here. Let's say that this whole system is 4 meters long. Let's say this guy's standing 1 meter from the edge, and this here is going to be 1 meter from this edge. Now, because I have locations of objects, I can solve this using torques, because assuming that nothing snapped and the whole thing isn't rotating, the net torque has to be equal to what? 0. So I'm going to rewrite this. Torque net. Now, there's no dimension for torque because it's a circle. Is going to be torque of tension 1 plus torque of tension 2 minus the torque due to gravity on the can minus the torque due to gravity, one of these should be a person, on the person, minus torque due to gravity of the scaffold, had better be equal to 0 or this guy's going for a fall. Do you really want to complicate it that hard this already? We could, but we won't yet. All right. So then looking here, this would be force tension 1 times radius plus force tension 2 times its radius minus, I wanted force of gravity on the can times its radius minus force gravity on the person times its radius minus force gravity on the scaffold times its radius equals 0. Now, we've got a whole bunch of r's now. Not all of these r's are the same. Each of these r's is relative to the axis of rotation of the object. So each one of these r's is measured to the axis of rotation of the scaffolding. Okay, where's the axis of rotation of the scaffolding?
All on the end.
Okay, I've got two answers. I've got center of mass and I've got on the end.
On the end.
Depends on how you identify it.
It's like,
Okay, so we could talk about it as a plank. I could see where you're getting that, add this to pencil. Okay, so one end busts off and it's a pencil. Okay, but it's not. It's holding. One of the convenient things here is that Newton's second law for rotation must hold true regardless of where we address the axis of rotation to be. Especially since this is all 0. Maybe the axis of rotation's here. Maybe the axis of rotation's here. Maybe it's here. Any of them are a valid assessment of the axis of rotation of the object. Because if any of them have a net torque that does not come out to be 0, then this thing snaps and things start spinning. So it doesn't matter where we address the 0 to be. It has to add up to 0, otherwise things are in motion. Okay? So what we're going to do to simplify this is we're going to identify an axis of rotation that simplifies things for us. Because we have two other unknowns. What are our two unknowns in the problem? Force tensions, right? So we don't know this force tension, we don't know this force tension. So where would be an ideal spot to say the axis of rotation is? Well, if it's rotating around the center, then I still have two unknowns that I have to solve for. Pick one of the ends. I'm going to pick one of the ends because then what's the radius to that force tension? 0. So I'm just going to go ahead and place my axis of rotation right here. No, they're not, because think about if you try carrying something with someone. Let's say that it's a fish tank with water in it, and you're going upstairs. Do both people have to lift evenly? No, because the weight's shifted to one side. Same deal here. Okay, so we're going to assess that as our axis of rotation. So now I have force tension 1 times what radius? Plus force tension 2 times what radius? Minus force gravity of the can, so 50 times 9.8 times what radius? 1. Minus force gravity of the person, so 100 times 9.8 times what radius? 3. Minus force gravity of the scaffold itself, or 100 times 9.8 times what radius? Say again? In the middle, so 2. Oh, you said, can you move it up? Well, thanks for both. I do. Yeah. I blame it on the screaming infant. All right. This has to, as a sum, be equal to 0. All right. So why did I decide to hear that in the middle from over here? When we're addressing the forces acting on an object, we always consider gravity to act at an object's center of mass. Meaning wherever, if we measured the average mass location on this object would be at the center. You can think about it in terms of where would you place it to try to balance it. Like a pencil, if you're trying to balance it on, one location, where are you going to hold it to get it to just rest evenly? That's the object's center of mass. That's where its force of gravity acts. Okay? So the same thing works here for determining where its torque will act. From here, you can solve for force tension too, correct? Questions about solving for force tension 2 from this spot?
Okay, so force tension 1 is canceled out because that's our whatever.
It's at our axis of rotation. So because R is 0 at that spot, well then the torque due to that tension is 0.
If you put it in the middle though,
Then you've got two unknowns. Good luck solving.
okay, so you have to put out the
You have to put it at an end. Now this gives me my force tension 2 here. I could then use that in my forces equation to find my other force. Or I could write another torque net equation where I just put the axis of rotation over here. And I solve for the remaining torque. Either way works. They all will come out with the same answers both times.